Good morning. We start the second tutorial, detecting materials and device structure by materials theory tools, computation and design, animated by Professor Mehdi Salmani. Mehdi Salmani is Professor Mehdi Salmani is from University of Mohammed Rabat, Faculty of Science. He received his PhD degrees from the same university in nanotechnology science and spectronic devices. He is a professor in the same university. The main interest topics of professor are quantum materials, nanotechnology science, geographics, environmental modeling, magnetocaloric effects, photovoltaic and electronic devices, ab initio calculation and Monte Carlo method in modeling and simulation of new materials for anthropology science. He contributed to over 50 conferences and he published about 20 chapters, book, and 70 papers in international leading journals. Now the floor is to Professor Mehdi Salmani.
So I am so delighted to be with you today, and thank you very much for having me in this workshop, which concerning the predicting materials and device structure by theory tools, computational and design. Today, we are going to talk about the density functional theory. What is density functional theory and what is used for? Also, we are going to talk about KKR-CPA code, which is one of methods of electronic structure calculation, and KKR and decay. So, we are going to talk about KKR-CPA codes, which are one of the methods of electronic structure calculation. The KKR indicates the initials of Korenga, Cohen, Rostocker, who invented these methods. So we are going to talk about density functional theory. What is density functional theory and what is used for? As you know, the density functional theory is a computational quantum mechanical modeling method used in many areas of material research. We can find this, for example, in physics, in chemistry, in nanomaterials, in surface calculation, in geophysics, for solving the Schrödinger equation, and hence to investigate the electronic structure and other properties, for example, the magnetic and optical properties. But first, let's start by some general information concerning these methods and the KKR codes. So, in this morning, we are going to talk about density functional theory. What is density functional theory and what is used for? Density functional theory is a computational quantum mechanical method used in physics, chemistry, material science, nanomaterials, biology, geophysics, to investigate the electronic structure. So, these methods is implemented in very many programs in order to solving the Schrödinger equation. We are, for example, when to calculate, we have also crystal, we have fleur, we have 1-2K, 1-2K, SPR, KKR, KKR-CPA VASP, which are the subjects of our workshop, and how and why to access these codes. Some of them are general or accessible by general public licenses, whereas others are proprietary. So, how to choose these codes? The choice is based in different choice. For example, we have the basis sets, the potentials. The choice can be based in exchange correlation functionals, but also an algorithm for solving the Schrödinger equation. Today, we are going to talk about the KKR-CPA codes. KKR is one of the methods of electronic structure calculation. And KKR indicates the initials of Koringa, Cohen, and Rostocker, who invented these methods. And CPA means the coherent potential approximation. We can apply this code, for example, to calculate the electronic structure, the magnetic and optical properties, also to calculate the structural properties and the total energies and forces. What is hard to calculate with this code? It is hard to calculate, for example, the transport properties. For example, the thermal conductivity, electrical conductivity of insulator, rheology, and diffusion. Also, with this code, it is hard to calculate the excited electronic states, for example, in the case of optical spectra. Finally, it is hard to calculate the fluid properties. So, to compile this program, we need an input file. So, how and why to create these inputs? To create this input file, we can use Xband. What is Xband? The Xband is a tool which allow us to set up the various input file via input file menu. And the main parameters we need to create this input file for compilation of KKR code is the space group, lattice parameters, and atomic positions. These parameters are generally the crystal structure of materials, and we can get usually the input file to compile the program. As you say, this input file containing parameters which we are indicates the self-consistency. And after we have FCC. FCC indicates the type of variable lattice. We can have also FCC. We can have hexagonal. We can have also sample cubic and others. And also we have in second line the lattice parameters. concerning this structure. We have also 1.0. 1.0 indicates the width of energy contour. And after we have NRL, which indicates the relativistic effects. This parameter is very important. Why? Because simply in the case of rare earth doped materials, we should introduce the relativistic effects, or in the case of nanostructure, the relativistic effects is very important. After we have the WN ASA, which indicates the type of exchange correlations, LDA, local density approximation, or GGA. GGA is gradient generalized approximation. As you know, the choice between these approximations is depends of materials. For example, in transition metals, doped materials, we should introduce GGA or gradient generalized approximation. Whereas in the case of materials depends or doped by P-block, LDA, or local density approximation is very important. After we have the parameters MAG. MAG indicates the magnetic properties. These properties or these parameters is very important, for example, for spintronic application or magnetocaloric application. After we have H, Brillouin zone. And after we have 200, number 200 indicates number of iteration to get the convergence. Number 3, number 3 indicates N-type. What does it mean, N-type? How many of atom exists in unit cell? For example, in this case, we have the cables. Also, we have 27, which indicates the atomic number of cables. 100 indicates the concentration of these elements. In this case, we have 100% of cables. After we have the chrome doped by ions. We have 60% of chrome doped by 40% of ions. And the last one, we have the number 4. Number 4 indicates where each atom is. So, with this input, we can get all properties, for example, the magnetic properties, electronic properties, and optical properties, and others. For example, to get the electronic and magnetic properties, we have to replace GAU by DOS. What does it mean, DOS? DOS indicates or describe the proportion of states that are to be occupied by the system at each energy. Also, in the case of electronic and magnetic properties, we can replace GAU by SPC and get the Bloch spectral function. The band structure or the electronic band structure or simply band structure describes the range of energy level that electron may have within it. as well as the range of energy that they may not have, call it band gap or forbidden bands. Also, we can have the X-ray or magnetic X-ray dichorism. We replace GAU by XMCD. The magnetic X-ray dichorism is very important in physics. In one hand, it describes and providing information on electronic structural and magnetic properties of atoms. These properties describe the transition from a core state to an empty electronic state. In optics, the term dichorism refers to change in the absorption of polarized lights on passing through a materials in two different directions. The origin of the dichorism effects can be anisotropies in the charge or the spin in the materials. For example, the metals are usually ferromagnetic and their magnetic properties are best studied with X-ray magnetic dichorism. Also, we can apply the code to calculate FSM or fixed spin moments, which the total energy as a function of constrained spin magnetization. Why this properties is very important for materials? Simply, FSM procedure offers several advantages in studying ferromagnetic materials and facilitated the identification of metastable ferromagnetic phases. Based in CPA, coherent potential approximation, we can apply this code to calculate the night temperature. In the failed or in the main failed theory, the current temperature is evaluated as this formula, where Kb indicates the Boltzmann constants and EF and EMD are the total energy in the ferromagnetic and NMD states. But it is well that the main failed theory overestimates the Curie temperature. So, for more accurate Curie temperature, we should use the Monte Carlo modelization. So, in this case, we should calculate with the KKR-CPA the exchange interaction in a coherent potential approximation using the exchange interaction by the Eisenstein formula. So, as a conclusion, density functional theory is by far the most widely applied ab initio method used in 4 real materials in physics, chemistry, biology, geophysics, surface calculation, and material science. Approximate forms have provided to be very successful. But in the case with strong electron-electron collidation or localized electron, which is not correctly described by local density approximation or gradient generalized approximation, we should use the self-interaction corrected or LDA plus U approximation, which is considered as extension of local density approximation. that concludes my presentation. And thank you for listening. And now, if there are any questions, I will be pleased to answer them. Once again, thank you.
Salmani, there are some questions in the chat from Rizlan Academia. I see one question. She said that I have a question about the physical disagreement between the GGA and the DGA plus U approximations. I first did my calculations with the GGA and found an indirect gap gamma X. Once I performed calculation with GGA plus U approximation, I found that the graph changed from an indirect to direct nature, gamma minus gamma. Please, Professor, what happened in the material when we add potential until we get the gap nature changed?
Donc, thank you for the question. I think using GGA plus E, we should have the some results as experience. I don't understand why these students get in confusion between the experience and the calculation. I think the error is from the input file or the lattice parameters or structure. So he should to recalculate with GGA plus E, and I think get the good results.
Another question from Hajar Jami. She said, can you explain more do your parameter in DFT calculation, sir?
Okay, is in input file labels?
I don't know. Maybe should write.
So can I?
I will allow her to talk. Please, Hajar, raise your hand.
Use your mic.
Allows to talk. Yes, you have the floor, Hajar. Unmute your mic and talk. Hajar.
Do you hear me, sir?
Yes, we can hear you.
Hello? Yeah. I would like to ask you about the U parameter in DFT calculation. Can you explain more how it measures the localized electron and GGA fails to describe them?
Sorry, Hajar. Sorry. Can you repeat your question, please? Hajar? Miss Hajar?
I repeat?
Can you repeat your question, please?
I repeat my question.
Yeah.
I would like you to explain me more the U parameter and how it will describe the localized electrons and why GGA failed to describe them.
Okay. So to compile the KKR code, we start all our calculation.
Yes.
With Go. Okay.
Yeah.
So, for example, we need to calculate the magnetic or electronic structure. Okay.
Yes.
Okay. So
yes,
in this case, we replace Go by DOS or SPC, which DOS describe the density of states and SPC describe one structure, okay? For example, if we want to calculate the X-ray magnetic dichroism, in this case, we replace GAU by XMCD, and we get usually your results. Okay?
Okay.
Okay, Hajar?
Yes, thank you.
Okay. Concerning the approximation, for example. Okay, okay. You are welcome. Another question? Another question? Please, another question?
I should mute my mic. Yes, there is another question from Mohammed Youssef Messous. Can we calculate the emission spectrum as optical properties with this code?
Sorry?
Mohammed Youssef Messous asks if we can calculate the emission spectrum as optical properties with this code.
Yeah. Well, yeah. It's usually to calculate the X-ray magnetic X-ray dichroism. Yeah, with this code.
And another question from Mohammed Ashihbun. He asked, can you give us an example of the materials with the atoms that have the strong correlation electron-electron?
Yeah. For example, we can take a sample materials doped with transition metals. In these materials or in these elements, the correlation effect is very important. So in this case, we should use self-interaction corrected or the LDR plus U. Likewise, for example, the materials doped with rare earths. It's okay? It's okay?
I don't know. Okay, the Mohammed Youssef Messous returned back and he asked, what about the thermodynamic properties?
No, it is hard to calculate these properties with this code.
And is there any calculation limitation?
We should use another codes, for example, or another programs.
Is there any calculation limitation when atoms have a height z?
No, there is no problem with this code. Concerning number atomic, there is no problem with this code to compute this code.
I give again the floor to Hajar. Maybe he has asking again a question. Please, Hajar, unmute your mic. I see that you have posted a second question. I don't know if it is the same. The depth includes the change correlation term. Could you explain more this term and if it is approximate, it is this. I see that some questions are repeated. Mariam Bouchabun, he asked, can we create a spare cell with the KKR code?
There is a difference. There is a difference between some codes. For example, in the case of KKR-CPA subject of this workshop is based in unit cell. okay, which contain all information about the materials. Whereas for the case of Win2K case, CASTEP, FPLO, this code is based in supercell. That this is two different philosophy for this code.
Okay.
Okay.
Mohammed Ashabun, he asked, the geometry optimization did not converge. What should we do then?
To recalculate the systems and get and he will get usually the conversions.
Abdelhakim Nafidi, he asked, yeah. Yes, Abdelhakim Nafidi, he asked, at what temperature does calculations are done? And how to introduce?
Are done at zero.
Yes.
At 0 Kelvin.
Kelvin. How to introduce the effect of temperature?
At now, it is not impossible, but it is hard to introduce the temperature effects in the KKR-CPA code or code, for example, Win2K or CASTEP. It is a problem of temperature effects. So what we can do is to compile the program at 0 and doing after the simulation, the Monte Carlo modelization.
Abdelali El-Omrani asks how we can deal with the DFT plus Q in this code.
No. The equivalence, LDA, we can find it, for example, LDA plus B, we can find it, for example, in Win2K case, we can find it, for example, in CASTEP and others. But in this case, instead of the LDA plus B, we have SIC or self-interaction corrected, and we can get the similar result as LDA plus U.
Okay, the last question in Q&A. Can we have an idea about the reactivity of natural compounds by using DFT?
Sorry?
Leila Lasri asked if we can have an idea about the reactivity of natural compounds by using DFT.
Can he reformulate this question?
Nadia, please raise your hand, Nadia. I will give you the floor to ask him on live. Yes, allow him to talk, Leila. You have the mic.
Okay,
you have the floor, Leila.
Thank you so much. Thank you. Thank you, first of all, for your presentation. I would like just to know if we can use this computational modeling method to have an idea about the surfaces of some complex materials like polymers, natural polymers.
So, okay, I think it's the same probabilities as mentioned in my presentation in the case of fluid properties or thermal properties. It is hard for KKR-CPA code to calculate, I think, the surface properties. We should, for example, use another code.
For example, if you have an idea about the other codes.
I am so sorry, but I have no idea about the codes that calculates the surface properties.
Okay, thank you so much. Thank you.
Thank you. I will give the floor to participants who has raising their hand. I start by Abdelkader Saim. Donc, I allow him to talk. You have the floor, Abdelkader. I switch to Mohammed Isam Zian. Mohammed Isam Zian, you have the floor.
Yeah. Hello.
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 Thank you very much, Monsieur Abdelaziz, Mr. Abdelaziz.
You're welcome.
My question is, what are the advantages of this last code? The new features, for example, compared to other computational codes such as VN2K, for example. The second question: does this code does the calculation on all electrons, valence and cores, or only on valence electrons? And thank you very much.
Okay. Donc, to compare, for example, this code with the Win2K or other codes, this code is the only codes can calculate the random systems. Okay, and is a sorry.
Okay.
And in the case for doping, it's the doping. It is usually to calculate, for example, the materials doped with
other elements.
Exactly. Yeah. Exactly. And for the minimum of percentage. Okay. And in the other hand, this code calculates valence electrons and the core electrons. Okay.
All electrons.
All electrons. Yeah. Exactly. Yeah.
Thank you very much.
No.
And now I give the floor to Youssef Kinzi.
Thank you for this topic, this important topic. The question is, what code can we use for a study DFT for C2N H2 polyene?
Can you please repeat the question?
What code can we use for a DFT study for C2N H2 polyene? Yes.
I have a problem to hear you. Can you repeat, please?
What code can we use for a DFT study for C2N H2?
I suggest Kinzi to write to his question in Q&A.
Yes.
Okay. I switch to Ben Dawood. I see that he has raising his hand. Okay, and now I can't give the floor to Toi, c'est moi. Either El Mehdi, Salmani. I don't know if it is a identity usurpation here. Ben Daoud, you have the floor. I allow you to talk.
Thank you very much for your explain. Please, can you explain what is the difference between the ladle and the GGA?
Okay. The difference between LDA and GGR.
Yes. Thank you very much.
Okay.
Before your answer.
Okay. In the case of local density approximation, suppose the systems with an electron which is constant, whereas the GGA or generalized gradient approximation, we have a variant of electrons. So we have a terms of gradient. So this is in one hand. In the other hand, the LDA, for example, we can apply, for example, in the systems, or we have P block, whereas the GGA, we can use it in the case transition metals dope the materials. It's okay?
There is no new questions. I am waiting for the question, the previous participant is not in the Q&A. I will see if there is a question in the chat room. Okay, see you next time. There is no question. Yes, there is a question here from Ali Abjau. Please, what is the difference? The different SPPR and KKR-CPA.
Okay, I think the SPR KKR or KKR-CPA code is similar. So this is the same philosophy to compile or to get the results. Okay, but the developer is different. But the two codes, KKR-CPA or SPR KKR, the two codes treat the random systems. It's okay?
I do not see any new question. There, so we close this session of this tutorial. Thank you, Mr. Salmani. Thank you for all
we are welcome.
participants.